Okay. So as some of you have already noticed looking on Canvas, midterm 1 has been graded. The exams will be back in your hands in lab tomorrow. Here's the distribution of grades. So the overall average was just under 30 points out of 50, which is considerably better than it was last year. And this is a actually fairly significant improvement, especially because question 4 was a bear. Very few people got close to a right answer on that one, probably because you had exactly one other previous opportunity to practice with it. But for everything else, the averages hovered around 65 to 70%, which is great. So based on the algorithm that I use for assigning letter grades, if I were forced to assign a letter grade based entirely on your midterm 1 score, that's the letter grade I would give you. Okay, so you know, the mean is the cutoff between a B minus and a C plus. Every standard deviation is a letter. And the mean and standard deviations don't include those 2 people at the very top or those 2 people at the very bottom who get A pluses and Fs by rule. Now, if you see yourself, you see your score in one of the last 2 rows of this table, it's not the time to panic, but there is a problem. It may be that there is a problem with the way that we're teaching the class, that we're not addressing your particular set of skills or your particular background. It may be that there are some study habits that we need to change. It may be there's some fundamental misunderstanding that we need to address. Rather than just throwing your hands up and screaming, please come talk to me, come talk to the TAs. And I will make a prediction that most of the people who are in that block of students are probably trying to do the homework on their own, not coming to office hours, or sorry, either trying to do the homework on their own or letting the other people in their homework group do 2/3 of the homework. Not working with other people in the sense of actually discussing the problems. Hey, how did you attack this? What should I do? Versus what's the answer? Not asking questions on Piazza, not coming to office hours, partly out of a desire not to want to look stupid in front of the professor, the TAs, or the other students. Please, I know it's hard. I understand from personal experience the difficulty in trying to get past that barrier of not wanting to look stupid. Asking questions about fundamental misunderstandings does not make you look stupid. It makes you look smart. You recognize that there is a problem and you're working to address it. Sitting on it and saying, I'm not going to think about it, that makes you look stupid. Not talking to people makes you look stupid. And it makes you look stupid in an official way. You know, which is unfortunate because I don't believe anyone in this room, anyone in this class actually is stupid. Right? All of you were smart or you wouldn't be here. There's just some fundamental problem that hopefully talking to us we can help figure out how to address. If you find yourself up at the top, now is not the time to fall asleep. The class is about to get harder. If you find yourself up at the very top, now is the time to introduce yourself to people who might write you recommendation letters. And possibly, you know, think about whether this is something you want to do in a more professional capacity than just taking this class. Because when you're looking for recommendation letters or references for jobs or whatever, everyone is going to ask the same question. Okay, great, you got good grades, but what else have you done? And so if you're up there at the top, you're doing really well at this stuff, you might consider seeking out more opportunities to do it independently. Build up a little bit of a CV before you graduate. So in any case, no matter where you are on this list, if you have concerns, if you have questions, if you feel like you have a decision to make about whether to stay in the course or not, please come talk to me. In particular, I will recommend that Wednesday morning office hours, almost no one comes. So if you're around tomorrow morning, or if you're around next Wednesday morning, which is still before the drop deadline, that would be a good time to drop by. If that doesn't work for you, send me email. And also, if you don't want to talk to me, feel free to talk to the TAs. Feel free to talk to other people in the class. Just don't panic and run off into a cave like I did when I was an undergrad, and wake up just in time to fail the final exam, like I did as an undergrad. Okay. Any questions about the midterm? Okay. Otherwise, we're on the usual schedule of, there's a new homework out. It's due next Tuesday. Homework 4 was due half an hour ago. We're going to start doing this crowd grading thing, probably setting up a dry run at the end of this week, just to make sure that everybody can log on and that we know how to actually work the system, so that for homework 6, one of the things that you'll be asked to do on homework 6 is to submit one of the problems, in addition to submitting it on paper for the staff to grade, submitting it to the peer evaluation system, so that basically one of the problems will get looked at by 8 other people in the class. Right? So the idea is that each team will submit 3 times, or however many are on the team, their solution to, say, homework 6 problem 1, and then each person in the class will be shown 4 or 5 of these submissions and asked, tell me on a scale from 0 to 4 how correct you think this is. Tell me on a scale from 0 to 4 how clear you think this is. Give us a couple of sentences to say why for each one. And then after a few days, everyone will get their reviews back, and we'll get feedback. Mostly this is meant as feedback on clarity more than correctness, but actually getting feedback from other people in the class telling you how clear they thought your solution was may be more helpful and, if nothing else, more believable than the feedback that the TAs and I are giving you on the same thing. Again, you all are guinea pigs. This is something we're thinking about launching next semester with 400 students. So things are likely to be a little bit rough at the beginning, but I do think it will be a useful exercise. So stay tuned. Hopefully I'll have more concrete things to say about this on Thursday. All right. So on Thursday, we started talking about dynamic programming. And the examples of recursive problems that I solved with that can be solved with dynamic programming problems. We talked about the Fibonacci numbers. Here's the recursive part, and the recursive definition of the Fibonacci numbers immediately gives you a recursive algorithm that runs in horrible exponential time. Okay, come on. Go the other way. Okay, stop. Thank you. All right. But the reason why the running time of this algorithm is so horrible and exponential is because you're wasting a lot of time repeating work that you've already done. When you're computing the 8th Fibonacci number, for example, the recursive algorithm is going to attempt to recursively compute the 5th Fibonacci number 3 times, and the 4th Fibonacci number 5 times, and the 6th Fibonacci number 13 times. When you only need to compute it once. When you're computing the nth Fibonacci number as a subroutine, you only need to compute the n smaller, Fibonacci numbers 0 through n minus 1. You don't need to do an exponential amount of work. So rather than recursing your way down, a dynamic programming algorithm starts with the base cases, f0 is 0 and f1 is 1, and builds up to the more complicated cases, still following the recurrence, but in the opposite order from the way you think about it when you want to think about recurrences. Then I talked about longest increasing subsequences, where again you can define a recursive function that represents the length of the longest increasing subsequence in an array. And if you follow this recursive definition as a backtracking algorithm, you'll get something horribly exponential. But just like for Fibonacci numbers, where there are really only n distinct subproblems to consider, for longest increasing subsequence, there are only n squared distinct subproblems to consider. And so by writing the results of these subproblems into a two-dimensional array and filling this array in the appropriate order, you end up with an algorithm that runs in only n squared time instead of 2 to the n. Okay, so what I want to do today is go through a couple of examples of backtracking algorithms that we saw a week ago and show you how they can be turned into dynamic programming things, and then go through another extended example of developing a dynamic programming algorithm from scratch and talk about some of the other details that we've brushed over a little bit quickly, but just to show you the start to finish process of creating a dynamic programming algorithm. Okay, so one of the problems that we considered was the subset subproblem. You're given a set X of positive integers and a positive integer t, and the question is there a subset, call it A of X, such that the sum of all the elements in A is equal to t? Okay? Now, the recursive backtracking algorithm that we saw for this starts by picking an arbitrary element of X and saying, is there a subset that adds up to the t that contains this element? And then, is there a subset of X that adds up to t and excludes this element? So you have a binary choice. Do I keep this element or do I throw it away? And in each of those two cases, you can make the decision by recursively solving a subset sum problem on a set of size n minus 1, everything except your chosen element, either with the same target value t if you decide to throw the first element away, or a smaller value t if you decide to keep it. Okay, so if I want to be a little bit more concrete about this, I'm actually, in practice, I can imagine that my input is going to be represented by an array, right? When I say given a set, in reality, when I want to implement something, I have to define what that means. Now, some software libraries have data structures called sets. But when I talk about a set, I really mean I need the ability to extract an arbitrary element out of that set and somehow recurse on everything else. And the simplest data structure I can imagine that supports both of those things is a simple one-dimensional array. Okay? So I'm going to define a recursive function, first in English and then with a recurrence. So SS of I comma t, this is true. This is a Boolean function if and only if there is a subset A of the elements in X starting at index I and going up to index N whose elements sum to the target value T. Right? This is, if we imagine taking the array and deciding on a particular element to keep or throw away, the easiest element to think about is the one at the beginning of the array. So as I recurse my way down, I'm going to be throwing out more and more elements at the beginning of the array, leaving me with this suffix starting at some arbitrary index I. And so I'm going to just set up my recursive function to take that structure into account from the beginning. I'm going to do this deliberately instead of accidentally. And then pass in just that index I as the first parameter to this recursive function, rather than passing in a whole array, which, if you actually tried to implement it, would take a bit too long anyway. Okay, so now that I've defined this in English, I can give the definition as a recursive function. So there are a couple of base cases which we figured out last time. This is going to be true if the target value is equal to 0, because no matter what my set is, the empty set is a subset of it, and the elements of the empty set sum up to 0. It's going to be false if T is negative, right? If over the course of my recursive calls I reduce T down to something that's negative, then no set of positive integers has a negative sum, including the empty set of positive integers. Or if I've already thrown out every element of the array, right? So that last condition is what happens when the base case that we're going to run into if T is too big compared to the choices that we make as we recurse down. We're going to run out of set elements before we've exhausted T. And then otherwise, I have two choices. Either I just decide to throw away element A sub I and look for a subset of the smaller suffix that has the same target value, or I can decide to keep element A sub I, in which case the target value I'm looking for is now smaller by this value that I decided to keep. Okay? So here is my recurrence. And this is exactly the same recurrence that we came up with a week ago, written in slightly different notation. But we have the same binary choice in the most general case. Either we keep A sub I or we don't. This is, of course, otherwise. Okay? Now, now that I have the recurrence in hand, I can try to come up with a dynamic programming algorithm for it. So let me go through the checklist of things that I need for a dynamic programming algorithm. I need to be able to record the values of various recursive subproblems that I see along the way. Okay? So I have a function here that takes two integer parameters as input, and so I need a data structure that I can pass two integers and it will give me back a value. Can anyone suggest such a data structure? 2D array. Good. Okay. What are the dimensions of this array? And I'm deliberately not drawing it as a square. Okay. The rows are going to be indexed by I, and the size of the number of rows is going to be roughly, up to a plus or minus 1, depending on how you implement the base cases. There are n different values for that index I. Right? That index I is an index into an array of length n. It has to be an integer between 1 and n, or possibly n plus 1 for the overflow base case. Okay. Right? So the rows correspond to indices in the original array. How many columns are there? What's the other dimension? Well, how many different values can the second parameter have? T, whatever the original value of T was, the second parameter in the recursive call can't be bigger than that. And if it's smaller than that, it can't be too much smaller, or the answer is obviously false. Right? So the interesting values of the second parameter that I need to think about are between 0 and whatever the original value is. Right? So I have a, and maybe to avoid a little bit of notational confusion here, it might be useful to, use a slightly different variable here. Little t is a particular value that I encounter as I recurse. Capital T is the original input value. Okay. So a particular point in this array is going to be accessed by telling me the index I, where does the suffix start, and the target value, little t, which is somewhere between 0 and capital T. Okay. Second question. Evaluation order. There's a minus here. That's getting a little obscured. Okay, so if I were to implement this as a recursive algorithm, but slap this memorization wrapper around it, whenever I find an answer to a subproblem, throw it into the table. Whenever I make a recursive call, look in the table first. The values in the table would get filled in some order. Yes? Okay, so, right, notice when you recurse, you always recurse on a larger value of I, right? So one of the recursive calls is a larger value of I, but the same value of T. And one of the other recursive call is a slightly larger value of I and a smaller value of T. I don't know what the smaller value of T is, but just know that it's smaller. And so as long as I evaluate every row completely before I start on the previous row, then when it comes time to fill in that blue box, the pink boxes are already there, and I can just do one OR. Okay? So the evaluation order is, the outer for loop considers the rows one at a time in order from bottom up. And the inner loop, well, it doesn't matter, actually, but I might as well make it left to right. Okay? So if I want to write this as code, be something like this. Okay, and that scribble down there is just you just repeat the constant amount of work you need to evaluate that recurrence. Last step. What's the running time? Yes, sorry. I'm sorry?
Explain the drawing again.
Okay, so the double arrow is the outer for loop, and the single arrow is the inner for loop for the big arrows. Maybe I should draw this, the dependencies all in blue, just so that maybe it's a little bit clearer. Okay, so the outlined box I'm trying to think about how to develop this order. So I pick an arbitrary spot in my data structure. That's the outlined box. And then I ask what values elsewhere in the data structure do I need to compute the value that goes here. Right? And the two values I need are the one immediately below it and in the next row below and somewhere to the left, but I don't know where. Okay. And since those are my only dependencies, it doesn't really matter what order I look at within each row. I don't have any dependencies between elements in the same row. But I need to consider the rows in order from bottom up. And that's what the pink arrows represent. Okay?
Could we reverse the order of the loops?
No. Well, hang on. Actually, in this case, yes. You could reverse the order of the loops in this case. In general, you won't be able to do that. You can reverse the order of the loops because I've done the row loops from left to right. Right. I could also do the row loops from right to left, in which case I would not be able to swap which is inner and which is outer. Okay, good. Running time? Here's the algorithm. What's the running time? It's n times t. Now, I heard somebody say n squared. This is a really, really, really common mistake. When you're analyzing algorithms, all variables are not n. T could be smaller than n. T could be bigger than n. T could be exponential in n. T could be quintuply exponential in n, 2 to the 2 to the 2 to the n. All right? There is no relationship whatsoever between n, the number of elements in my input array, and t, the target sum. None. So you can't merge them together into a single variable. You have to keep the two variables separate when you're evaluating the recurrence, when you're evaluating the running time. So in particular, notice when t is some polynomial, say t is n squared. This gives you an algorithm that runs in n cubed time, as opposed to the recursive algorithm, which runs in 2 to the n time. Right? So this is faster than backtracking. When t is, well, let me just say, is reasonably small. I'm being deliberately vague here. On the other hand, if you notice, if t is 2 to the n, maybe my numbers are just really big. T is 2 to the n. This is slower than the recursive backtracking algorithm, which always runs in time t to the n. And here, when t is 2 to the n, it runs in time n times 2 to the n. Right? But slower when t is ginormous. Yes, that is actually a word in the OED. Okay? This is one of those circumstances where, because you have this other weird parameter in the running time, sometimes the dynamic programming algorithm is faster. Sometimes the dynamic programming algorithm is slower, right? In most cases of subset sum, or sorry, I shouldn't say most. In a lot of cases of subset sum that are actually show up in the wild, T is actually reasonably small, and this is the approach that you want. But you know, in the theoretical worst case, there's actually no way to avoid some kind of exponential behavior in something because the problem is NP hard. The hard instances show up when T is really enormous, and so it needs a lot of bits to represent. And so this ends up being still exponential in the number of bits I need to write down the numbers. Okay, if that went past you fast, don't worry about it. We'll bring it up again when we talk about NP hardness. Okay, so starting with the recurrence, we come up with a memoization structure. There are two parameters in the recursive function. They're integers that suggest a 2D array. The sizes of the 2D array represent the range of values that I can put into those two parameters. One of them is an index into my input array that's somewhere between 0 and n. The other is a target sum. It's somewhere between 0 and my original target sum, capital T. I figure out what the dependencies are between you know, a particular item in that data structure. What does it depend on? Well, things in the next row down. And that implies that I can fill in the table by considering the rows in order from bottom up. And then finally, because I'm filling in an n by t array and constant time per entry, the running time of the algorithm is order n times t. Okay. Questions? All right. Let me go through the other example that we did last week. We're given an NFA and we're given a string, and we want to know whether the NFA accepts the string. Okay. Okay, and the way we approach this is we said, well, look, the way I'm going to decide how an NFA accepts the string, I'm going to look at the first character. There are lots of options for how the NFA could transition when it reads the first symbol. I'm going to try each of them. And then I'm going to recursively see if the NFA starting in that new state accepts the rest of the string. And so my recursive subproblem is not going to be, you know, the NFA starting at state S for the whole string Q, but rather I'm going to define a function here. Again, this is a Boolean. This is true if and only if M accepts the suffix starting at character I, assuming that the NFA starts in state Q. Okay? So initially, I'm going to pass in I equals 1 and Q equals S, the start state of the NFA. Right? All right, so I defined a recurrence for this function. All right, so there are a couple of possibilities. There are a couple of possibilities to think about for the string. Remember, the definition of a string is it's either empty or it's a symbol followed by a string. So those two cases are going to show up in my recurrence. So there are two possibilities here. One is the string is empty. And when the remaining string is empty, that's going to happen when this index, where I want to start the suffix, falls off the end of the string. And when I'm in the, if I'm thinking about the empty string here, what is the value of this function accepts when the string I have left to read is empty? Right, it's the Boolean value Q in A. Right, this is a statement which is either true if Q is an accepting state or false if it isn't. If you want to, write this maybe slightly more explicitly, you could say true if I'm faced with the empty string and I'm in an accept state. False if I'm faced with the empty string and my current state is not an accepting state. Yes?
What about the epsilon region?
I'm assuming here an NFA with no epsilon transitions, because epsilon transitions make this problem harder. All right, so do the pre-processing you need to do to get rid of epsilons if they're in there. Otherwise, I have to try all possible values, all possible states that I can get to in one step from state Q reading symbol WI. Right? That set is called delta of QWI. Okay? And so for all states R in that set, this is a big OR, I'm going to ask, does the machine accept the suffix starting at I plus 1 starting in state R? Okay. So that big V, that is the logical OR version of a big sigma that means plus, or a big pi that means product. It means over all elements of this set, delta of QWI, for each one of those elements, I ask, if I go to that new state R and recurse, am I going to reach an accept state? If any one of those recursive calls says yes, I return yes. If all of those recursive calls return no, I say no. Okay. All right. So when I'm looking at the, that's the come up with the recurrence part. Again, this is the same recurrence that we came up with a week ago, perhaps with slightly different notation. Okay, so I need a memoization structure. How do I memorize this function? A tree. What are the nodes of the tree? Why a tree?
Because you could have a state that
Well, okay, so intuitively what I think you're thinking about is essentially the recursion tree of that recurrence, right? I don't want to do that because the whole point of doing the memoization is that different nodes in the recursion tree might actually correspond to the same problem, the same I and the same Q, right? So I need a memoization structure that does the merging of those equivalent things sort of automatically. Yeah. A 2D array. Amazing how often this is the answer. Okay. All right. So I'm going to be I'm going to index the 2D array by the index I into the input string and the state Q. Now, I want to explain why this is exactly the right answer. If you are actually going to implement a DFA, you need some way of representing this function delta, the transition function that tells you when you're in state Q and you read symbol A, you should go to this new state R. the most natural way of actually implementing a DFA or this transition function is by saying, okay, I'm just going to number the states from 1 to some number q. I'm just going to number the symbols in my alphabet from 1 to some number s. And then I'm going to keep a big s by q array that allows me to index in and look up the values, right? So it's actually fairly natural to imagine that the way the NFA is given to you is that this array delta here, or this function delta, is actually given to you in the form of some sort of array indexed by, along some dimension, by the states. So the states q are already small positive integers in some range from 1 to something. Okay. Now, this isn't the only way that you could be given the NFA. Another way that you might be given the NFA is in some sort of graph data structure. We'll talk about graph data structures in a couple of weeks, but essentially you have a record that corresponds to every vertex and maybe a pointer to records that correspond to each of the outgoing edges from that vertex. But even when you're given a graph data structure, notice what I just said. You're given a data structure that has a record for every vertex, and those records in an adjacency list, if you've heard of that, are stored in an array. So the vertices, even if you're given a graph data structure as your representation, the vertices of that graph will be represented almost certainly by indices into some sort of array, right? So using those indices also as to access the memoization structure is completely natural when it comes to actually implementing this stuff. Okay? All right, so I have some array whose size is n by however many states there are. Okay? Now, let's look at a particular spot in this array, indexed by I and q, and think, what do I need to evaluate first before I can evaluate that spot in the data structure? If I want to know the value of accepts IQ, what other values of accepts do I need to know first? Everything in smaller indexed states, everything below. Right? Remember, the I is indexed here, top down, in increasing order. I need to know actually not necessarily everything, but some subset of the things down here. I don't know what subset. It's going to depend on the actual value stored in the transition function. Which I don't know in advance because I haven't actually got the explicit transition function. But whatever the transition function is, all the values that accepts IQ depends on are of the form accepts I plus 1 something, which means each entry in this matrix depends only on entries in the next row. Hey, we've seen this before. So if I want to evaluate this, all I need to do is make sure that I consider in the outer loop the rows of this matrix in decreasing order. And within each row, it doesn't actually matter. Right? So the main loops are going to look something like this. You know, for I goes from n down to 1, and then for all states q, whatever. I don't care whether you consider them in index order from bottom up or from top down, because there's not really a natural ordering to the states anyway. It's just there's a convenient ordering that I used because of the way it was represented in memory, but that order is not really important. And then inside this double-nested loop, I'm going to evaluate the recurrence, which is going to involve a third nested loop. And then a constant amount of work inside there. Right? Now, this is a different form of recurrence than we've seen before, because in order to actually evaluate it, we don't just take two things and compare them. We don't know how many subproblems we have to look at. So, can you give me a bound on the running time? How fast is this algorithm in the worst case? Yeah. What's I? I think you mean n, right? I is an internal variable. It's not something I can talk about at the outside of the algorithm. But it's n times the number of states squared. And again, there is no relationship at all between the number of states in the machine and the number of symbols in the input string. Now, generally, you want to do this for a fixed NFA, and you want to do one NFA and lots of different strings. So you might want to hard code the NFA into the algorithm, in which case this number of states becomes a constant. A constant is some number that you figure out at compile time, as opposed to n, which is something you figure out at runtime. And if your NFA is in fact fixed, right? For example, you built an NFA to accept, let's say, C comments. You're likely to feed in lots of different pieces of text to see whether they're actually C comments or to strip the C comments out. Then the running time of your algorithm is going to simplify down to order n. The language of C comments has an NFA involving some constant number of states. Okay, but more generally, if you're building, an NFA compiler of some sort, then you can't think of the number of states as a constant, and so you have to keep it in the running time. Okay? So, given an NFA, given a string of length n, I can decide whether the NFA accepts that string in time, linear in the number of symbols in the string, and quadratic in the number of states in the NFA. Questions? So the only thing that was a little bit different here than the previous one is that the time it takes to actually evaluate this recurrence is no longer constant. I'm no longer spending a constant amount of time at every position in the array. I'm spending linear time in the number of states. All right. So the last problem I want to talk about, just to try to go from build up something from scratch. This is a problem that was, I first encountered back when I was a little kid, and my dad worked in the computer lab in the physics department at the university where he grew up. And they had these strange-looking screens called teletypes. And the teletypes had very, very slow memory. They were really slow devices by modern standards. And now I recognize, by modern standards, a slow device is one that you can actually see working. Right? Where every movie that involves a computer sending messages to another computer, you see this green text that goes across the bottom of the screen. You hear that dee-dee-dee-dee-dee-dee noise that you've never heard in real life, ever. This is where it comes from. Okay, that's what teletypes look like. Except unless you were insane, you never actually turned on the dee-dee-dee-dee function. the words would actually come across the screen very slowly. But it had some sort of internal memory to keep track of what characters were on the screen at any given time. And people were very clever. They developed these hardwired mechanisms to modify what was on the screen rather than, if I wanted to change what was on the screen, rather than just writing it over from scratch. Right? So, for example, if the word money was on the screen, I wanted to turn that into food, I might issue a command to the teletype to say, okay, move the cursor here, now change the current thing at the cursor to an F, move the cursor to the right, move the cursor to the right, delete that function, moving everything to the right of the cursor one step left. It was a very fast memory copy operation internally. Now change the character under the cursor to an O, move to the right, change the character under the cursor to a D. Okay, so there were these library calls for moving the cursor around, that little blinky block that you see in VI and Emacs and a few other things that's been replaced by a vertical line in most WYSIWYG stuff. The reason why that's a block is because that was where the TTY could apply the command. Change this character, delete this character by shifting everything left, insert a character by moving everything to the right, delete everything below, insert a line, delete a line, a few other operations like this. And so a very natural question became, given a string of text on the screen, how quickly can you transform it into a different string of text that you want to be on the screen? Right? So given the string money, how quickly can I transform it into the string food, where the elementary operations I'm allowed to perform are replace one character with another, delete a character from the string, moving things together, or insert a character into the string, spreading things apart, and that's it. Okay, so I can do insertions, I can do deletions, and I can do replacements. And using a sequence of insertions, deletions, and replacements, I want to transform one string into another. Now, for the last 30 years, this has not actually been a problem. Screens are fast enough, machines are fast enough that now when you want to change the text on the screen, in the background is probably being erased and redrawn about 50 times a second without you noticing. It's completely blindingly fast, partly because you're really dealing with a relatively small amount of data. But one of the places where problems like this come up a lot is in biology, right? Where now instead of money, you should imagine that perhaps you're looking at the genome of some sort of organism, and you want to know in evolutionary terms how different is this organism from some other organism. So given the DNA transcription of a monkey and given the DNA transcription of, what should the other one be? A bunny, good, food. Don't eat the bunnies that hop around. There are bunnies everywhere. Don't eat the wild bunnies. They have worms, supposedly. You'll get sick. There are farms that grow bunnies if you like that sort of thing. They used to sell them at the Urbana Butcher Shop, but unfortunately the Urbana Butcher Shop closed perhaps partly because there wasn't enough of a market for rabbit. How many mutations do I need to apply to this string of DNA to transform monkey DNA into bunny DNA? Okay, so let me be a little nicer to the vegetarians in the audience. Come on, Y? There's got to be another Y. Oh no, there's only one Y in the Scrabble set. All right. Right there. Okay. how many transcriptions, how many changes do I need to make to monkey DNA to get bunny DNA? And then we know that, in fact, bunnies did not evolve into monkeys. But bunnies and monkeys both evolved from a common ancestor. And so biologists use the mutation distance between bunnies and monkeys as a proxy for the distance from monkeys to the common ancestor and the distance from the common ancestor down to bunnies. Right? And now when you're talking about monkey DNA and bunny DNA, you're talking about strings of characters in a 4-character alphabet, A, G, C, and T, that are trillions of characters long. And so no matter how fast your computer is, doing something to terabytes of data is slow unless you have an efficient algorithm. Now, the particular operations that people use to model mutations are not as simple as let's delete one character, or let's insert one character, or let's replace one character with another. They're more complicated things like, let's take this block of DNA and that block of DNA and swap them, or let's take this block of DNA and just take it out in one step, or let's take this block of DNA and reverse it, because at some point the RNA went like this and then came apart in the wrong order. Nevertheless, the algorithm that I'm about to describe for the simple edit distance problem has generalizations that people use to really study the evolution of organisms, to study the evolution of languages, to study the evolution of all kinds of things. Okay. Now, one of the first things that we need is a way of actually, thinking about the function. So let me throw up another example, because I've actually worked out the answer for this example. So I need some way of thinking about this sort of unstructured problem. I've got 2 strings, and I can put in and take out symbols wherever I want. I need to impose some structure. Say T, and there's an H. All right. I think you can see where this is going. There's an M. It's close enough. H, 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 H. Okay, so this is an H. Okay, so I want to transform one of these strings into the other. I'm going to propose the following structure to encode the sequence of operations that I'm going to look for. I'm going to line the 2 characters up, the two strings up, one directly above the other, but I'm going to occasionally put in gaps between the characters that correspond to insertions and deletions. So the first 2 symbols of both strings are the same, so maybe the right thing to do is to leave those alone, and to represent that, I'll just stack them on top of each other. There's also the correspondence here between these R's and these I's. So I can maybe imagine a sequence of editing operations that I might encode like this. What this means is if I start with the word altruistic, and I want to transform it into the word algorithm. Really, is there no H? Are you? No. All right. Maybe this looks a little bit more like an H. What I'm going to do is I'm going to leave the A and the L alone. I'm going to replace the T with a G. I'll insert an O, leave the R alone, delete the U, leave the I alone, delete the S, leave the T alone, replace an I with an H, and replace a C with an M. So when I have a character in the second row but not the first, that corresponds to an insertion. When I have a character in the first row but not the second, that corresponds to a deletion. And when I have different characters in the top and bottom, that corresponds to a replacement. So this particular 2 by whatever array of characters corresponds to 1, 2, 3, 4, 5, 6 editing operations. Replacement, insertion, deletion, deletion, replacement, replacement. Okay. Delete, replace, replace. Okay? And so this is the structure that I want to imagine trying to find. Given the 2 strings, I want to find a structure that looks like this. There's gaps in this first row, maybe there's gaps in the second row, maybe it doesn't have gaps in either, but it could, of minimum total cost, where cost is the number of columns where the 2 characters don't match. Okay? Does everyone kind of see what how I'm phrasing the problem now as something of the flavor of find an optimal sequence of some sort? I'm looking for a sequence of character pairs where the first thing in the pair comes from string 1 and the second thing in the pair comes from string 2, or in either case is a blank, that minimizes some cost function. Okay? So I need if I want to set this up as a dynamic programming problem or as a recursive backtracking problem, I need to think about having some sort of decision that I might make that will leave me with a problem that I can pass off to the recursion fairy. And since the problem is find a sequence of something, the decision that first pops into my head is, well, a sequence is either nothing or it's a thing followed by a sequence. So if I can just figure out what the first thing is, I can let the recursion fairy find the rest of the sequence. So my question, the question that I'm going to try to answer is, what is the best first column? What is the best first pair? And there are 3 possibilities. The first column could contain the first symbol from each string, as it is in this example. It could be that, I don't want to think about the rest. The rest is going to be the recursion fairy's problem. The first column could look like this, where I have the first character in string 1 and the first character of string 2 together. It could be that it looks like this, where the very first thing I'm going to do is delete the first character of string 1, and then I'm going to recursively do the editing for everything else. Or the first column could look like this, where the very first thing I do is insert the first character from string 2, and then recurse on everything else. Now notice, when I inserted that character, the number of symbols on the screen went up, but nevertheless the problem size went down, because when I only recurse on these shorter strings. Once I've decided to insert the character, that character is no longer part of the input. Okay? So, 3 choices. I can either do a replacement, or I can do an insertion, or I can do a deletion. And when I recurse, I'm going to recurse on suffixes of the 2 input strings. Okay? So now this lets me think, my recursive subproblem is going to be, given a suffix of string 1 and a suffix of string 2, what's the best way of matching them up? So I'm going to define edit of ij to be the edit distance. This is the number of operations that I need to go from one string to the other between the first string starting at symbol I and the second string starting at symbol j. Right, so I'm imagining that I'm given 2 strings A and B as input in arrays. The first string A has length m, the second string B has length n. Okay. All right. Now, in the generic case, I'm going to have three possibilities for what I can do. I can either match up the first character in that suffix of A and the first character in that suffix of B. So I can try to match up AI with BJ to do a replacement. When I recurse, so this is going to be three possibilities. I don't know which one is best, so I'm going to take the minimum. So if AI is not equal to BJ, this replacement is going to cost me one replacement operation. If AI and BJ are the same, then this is going to cost me 0 operations. So again, a Boolean statement in brackets means the value 1 if the statement is true and the value 0 if the statement is false. And then when I recurse, I'm going to look at slightly shorter suffixes, starting at I+1 and J+1. The second possibility is I can do an insertion. Well, let me do deletion first. I can delete the first character of the first string, in which case I'm left with a suffix of string A starting at index I+1 and a suffix of string B starting at index J. Or I could do an insertion of character BJ, in which case now I've decided to use that symbol at the cost of doing one insertion. And now I want to recursively figure out the distance between the same suffix of A and a slightly shorter suffix of B. Okay, so this is the formulation of the sort of generic case of my algorithm, where I've got long strings. I'm somewhere in the middle of figuring it out. And I've got three possibilities. The first thing I can do is a replacement, which may or may not cost me anything, or I could do an insertion, or I could do a deletion. And each insertion and deletion costs me 1. I have no idea which of these three things is going to be the right one, so I'm just going to try them all. Now, can anyone imagine what the base cases are? I have a recursive function on strings where I chew away the strings from the beginning, and so I'm recursing on suffixes. The base cases are pretty much always the same. Empty, okay? And the way, again, that empty things are going to be represented is, one possibility is that A is empty. I've already decided what to do with each of the symbols in A. The other possibility is that B is empty, okay? What's the value of the edit distance function? So how long does it take to turn Rust into nothing? How many operations do I need? 4. Delete, 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 delete. All right? So if the second string is empty, the edit distance is the length of the first string. Similarly, if the first string is empty, the edit distance is just the length of the second string. Now, as a sanity check, how long does it take to turn nothing into nothing? 0. Now, how does that reflected in this function? That would be I is equal to m plus 1 and j is equal to n plus 1, in which case both of these base cases apply, and both of them give you the correct answer 0. Good. Now, this is the recurrence. All right. Now, I'll let you in on a secret. When you're developing these recurrences, it actually ends up being somewhat cleaner if you imagine chewing things away from the end instead of from the beginning of the string, partly because you avoid these kind of weird off-by-one errors that come up in the base cases. So if let me change the notation slightly. If instead of considering a suffix that starts at index I and a suffix that starts at index j, I consider prefixes that end in indices I and j, I get this very slightly cleaner recurrence, where now the base cases are a little bit more natural. Now I is the length of the prefix, and if that length is 0, that means the prefix is empty. And the result should be the length of the other prefix. Okay? Good. So let's go through the other steps. What data structure should I use to memorize this recurrence? 2D array. I, which can be anywhere from 1 to m, and j, which can be anywhere from 0 to n. And now any particular spot in this table is going to depend on a few nearby spots. Same row, next column, same column, next row, and next row, next column. Right? So I need to evaluate the solid stuff before I get to the hollow one. So what order should I evaluate this array? What order should I use here to make sure that the solid pink stuff is examined and filled in before I get to the white square? Yeah, I kind of want to head in this direction. And there are a couple of different ways that I could do that. I mean, I could go diagonal, 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 diagonal. But it's actually a little bit simpler just to say, I'm going to look at the rows from right to left, and I'm going to look at the columns from bottom up. So I'm just going to do both the rows and columns in reverse order. And in this case, it doesn't actually matter whether the rows or the columns or the outer loop. And then in the end, the running time is going to be n times m, because I'm filling in an n by m array, and in each position in the array, I have to do 3 comparisons and a couple of additions. And so in the end, you get an algorithm that looks like this. This is for the prefix version of the recurrence rather than the suffix, but that's a minor difference in the actual code. So for the prefix version, all the dependencies go down into the right, and so you can just do a standard double nested loop. You get this nested for loop thing as the result, and if you actually run the algorithm for those 2 strings, you get the answer 6. This is the actual table that you get when you actually run the algorithm on those 2 strings. And one of the things that I talk about in the notes is once you actually have those numerical values, you can use it to backtrack your way through the values to figure out what the actual sequence of editing operations should be. Just essentially by finding a path from the base cases to the final answer you want through the table. Right? I'll let you guys look at the notes for this, but this is the main reason why when I say, find the optimal thing, it's fine just to say find the cost of the optimal thing, or the value of the optimal thing. Yes? The link to the notes is broken. Okay, I will fix that. Sorry. All right. See you.